the low latency and high reliable broadcast communication for 5G V2X services. Abstract. In this paper, we consider a dense vehicular communication network where each vehicle broadcasts its safety information to its neighborhood in each transmission period. Such applications require low latency and high reliability, and thus we exploit non-orthogonal multiple access to reduce the latency and to improve the packet reception probability. In the proposed scheme, the BS performs semi-persistent scheduling and allocates time-frequency resources in a non-orthogonal manner, while the vehicle autonomously performs distributed power control. We formulate the centralized scheduling and the resources allocation problem as a multidimensional stable roommate matching problem, and develop a novel rotation matching algorithm to solve it. Simulation results show that the proposed scheme outperforms the traditional orthogonal multiple access scheme in terms of the latency and reliability. With the rapid introduction, with rapid development of vehicular networks, a growing number of applicants have emerged to improve the driving experience. Among various applications, safety critical services play a vital role, supported by the vehicle to everything V2X communications. To achieve low latency and high reliability LLHR for the V2X services, the long-term revolution LTE networks have been considered as a very promising solution by exploiting the device-to-device D2D communications. However, the existing LTE networks are based on the orthogonal multiple access OMA techniques and have not fully utilized the limited spectrum resources. This may lead to the severe data congestion and low access efficiency in dense vehicular network. To handle the challenges of access collisions and massive connectivity, non-orthogonal multiple access (NOMA) schemes have been introduced as a potential solution for 5G wireless networks, which allow users to access the channel non-orthogonally, capable of achieving high overloading transmission over limited resources. NOMA provides a new dimension for V2X services to resolve the congestion problem, especially in a dense environment, thereby reducing the latency. In this paper, we consider V2X broadcast scenario where every vehicle needs to update its safety information to the neighborhood in each transmission period. Each period consists of multiple time slots and then transmitter receiver. TXRX selection needs to be determined for each slot such that all vehicles can update their safety information in at least one slot during this period. Sub-channel allocation in each time slot is performed to manage the co-channel interference caused by non-orthogonal nature in NOMA. Moreover, to successfully decode the superposed received signals, an efficient real-time power control method should be applied by users. New challenges are thus posed in design of scheduling and resources allocation schemes. To tackle these challenges, we propose NOMA-based mixed centralized distributed NOMA-MCD scheme for cellular V2X broadcasting. The centralized semi-persistent scheduling SPS is performed by the BS, where the TXRX is selected and the time and frequency resources are allocated periodically in every few transmissions. For the BS, TSRX selections and the resource allocation problem can be formulated as a nonlinear integer programming problem to maximize the packet reception probability of the network. The distributed power control is performed by each user. To resolve such combinational optimization problem on TXRX selection and source allocation, we decoupled it into two multidimensional stable roommate MDSR matching problems, where the vehicle and time slots sub-channel are considered as two sets of students and rooms, such that multiple students can occupy the same room. We developed a novel rotation matching algorithm for the MDSR problem, which converges to stable matching simulation results show that our proposed NOMA MCD scheme performs better than traditional OMA scheme. fieldwork has discussed how to improve the performance of the safety critical applications from NOMA-based perspective. OMA in the 9 Resources Management for D2D Unicast Safety Critical Vehicular Communication has been discussed in 10. A centralized sub-channel allocation scheme involving several D2D broadcast groups underlying cellular networks has been proposed by utilizing upgraded algorithms. System model V2X transmission. The rest of this paper is organized as follows. In section 2, we describe the system model and propose the NOMA MCD scheme. In section 3, we formulate the centralized SPS of BS as a packet perception probability maximization problem and solve it by utilizing the matching theory. In section 3, an iterative signal control scheme is designed for the distributed power control problem of TX users. Simulation results are presented in section 5, and finally we conclude the paper in section 6. Section 2, System Model and Scheme Design. In this section, we present the system model of the cellular V2X broadcasting system and propose the NOMA-based cellular V2X broadcasting scheme to reduce access collisions. A scenario description. Consider an urban V2X broadcast system as shown in Figure 1. In every transmission period consisting of multiple time slots, each of n vehicles broadcasts safety critical information to its neighborhood in at least one time slot. The pedestrians always act as RX users in each time slot. Direct data transmission between neighboring users is achieved by the D2D communications. The available bandwidth is divided into K sub-channels for transmitting. Due to the dense topology of the network, when more than the TX user is 1 and then TX user 2 in Figure 1, are assigned the same time frequency resources, collision may occur for the RX users. RX user 1 located in the overlapping region of adjacent TX users' communication ranges. To reduce the probability of the collision as well as transmission delay, NOMA is then considered such that one sub-channel can be occupied by multiple TX users simultaneously. 11. Each conflict RX user, and such as RX user in Figure 1, utilize the SIC techniques, decode the received superposed signals, thereby avoiding the collisions. NOMA-based collision avoidance channel model. Based on the NOMA scheme, the received signal of RX user M over sub-channel K in time slot I. The I's time slot of transmission period is like this, where n denoted the index set of users within RX users M's communication range of interest. For example, a disk of a radius R is binary variable to indicate where user J is TX user transmitting over sub-channel K in time slot I. P JK is the transmission power of the TX user J. H denoted the channel coefficient of sub-channel K between TX user J and RX user M in time slot I. Represent the transmitted symbol. NM is the additive white Gaussian noise, AWGM, for RX user M with avoidance sigma n square. In equation, the channel coefficient can be expressed as denoted fading distances dependent pass loss respectively, with the representing the distance between two users J and M slot I. SIC decoding. The transmit power of the link corresponding to the conflict RX users will be carefully adjusted according to the NOMA principle. Each conflict RX user M decoded the received signals in the decreasing order of channel gains. For any conflict RX user M, the achievable rate obtained from TX user J over subchannel K in time slot I can be expressed as where rho JMK represent the SNR of the signal of TX users J-RX user M link, and S is a set of active TX users causing interference when RX user M decoded the signal of TX user J. Third, critical for successful decoding. When any conflict RX user M receives signals from multiple TX users, too critical for RX user M to successfully detect the signal XJ received from TX user J over subchannel K in time slot IRI. The signals of the TX users with higher channel gains than TX user J are successfully decoded first. The second rate threshold of TX user J is satisfied. The above criteria can be mathematically expressed as like this, where is assigned a function and J implies that the channel gain between active TX user J and the RX user M is higher than between TX user J and RX user M. NOMA-based mixed centralized distributed scheme. Based on the above non-orthogonal manner of reducing the collision, we aim to design a scheme where each user can successfully broadcast safety information to as many neighboring users as possible. While satisfying the latency requirement, we then propose the NOMA MCD scheme consisting of the following two phases. First, centralized TX RX selections and then time frequency resources allocation of the BS. Second, distributed power control of users, centralized TX RX selection and time frequency resources allocation of the BS. To avoid the non-negligible UR latency in the traditional dynamic scheduling, centralized SPS is considered in which the BS only updates the resources allocation scheme periodically. To be specific, the BS determines the TX RX selection and subchannel allocation of each time slot at the beginning of each SPS period. The resource allocation scheme then remains unchanged within each transmission period of the same SPS period. The centralized SPS can be performed by the BS based on the user's relative position information obtained from the periodical user broadcasting. Distributed power control of users. The NOMA scheme requires prior knowledge of the users for SIC decoding such as the real-time CSI, which is hard for the BS to obtain due to the mobility of vehicles. Distributed real-time power control of the users is then performed after the centralized SPS as the BS. In each time slot, the transmit power of the TX users is adjusted by themselves based on the feedback sent from the conflict RX users via control signaling. Third, NOMA-based centralized semi-persistent scheduling. In this section, we formulate the centralized TX RX selection and then time frequency resources allocation of the BS as a packet recession probability PRP maximization problem and then solve it by utilizing the matching theory. Problem formulation. Due to the time varying nature of CSI is a vehicular network, we adopt only partial CSI is centralized. SI, for example, H, JMK, I, JM, I to improve the reliability of the network. We try to elevate the probability of collision such that fewer retransmission are required, which in turn reduce the latency. Since the collision reduction can improve the PRP of the network, we then aim at maximizing the PRP of each transmission period, which is proportional to total number of signals successfully decoded by RX users. To be more general, we adopted the logistic function instead of the indicate function in third to depict the PRP. The probability that the signal of TX users J is successfully decoded by RX user M over subchannel K in the slot I is given as where rho is the slot parameter of the logistic functions. Based on the above discussion, the TX-RX selection and then time frequency research's allocation problem of the BS is one transmission period can be formulated as like this. Constraint OA denoted that any two users within each other's communication range cannot be TX users at the same time, since they will never receive each other's message while transmitting due to the half duplex nature. For the sake of user fairness, at most Tmax time slots are allocated to TX users is a transmission period as expressed in constraint OB. Considering the decoding complexity of SIC, we assume that each subchannel can be assigned to at most KU TX users within overlapping communication disks simultaneously as shown in constraint 5C. Matching algorithm design. To serve the above problem, we consider the users and time slot subchannel as two disjoint sets as students and rooms, such as multiple students can share the same room. As shown as constraint 7a, the time scheduling is considered prior to subchannel allocation for the users, and the time frequency resources cannot be considered as a whole. We then formulate the optimization problem in 5 as two MD versions and SR problems. First, the matching problem formulation for the TX-RX selection and time scheduling. We formulate the TX-RX selection and then time scheduling problem as two-side matching between the set of users and time slots. If a user is matched with the one time slot, we say that it acts as a TX user in the time slot. Otherwise, it acts as a RX user in the time slot, denoted the set of users as N and the set of time slots in the transmission period as T. Mathematically, a matching is defined as a mapping from the set into itself, such as rho, and any two users matching to same time slot are defined as matching pairs. User J prime are defined a forbidden pair in time slot of I if they cannot be matched with this time slot simultaneously due to the constraint 5a. The better describe the interaction between the users. We then investigate how each user selects each matching pairs. The key idea that each user tends to choose those far away from it as its matching pairs, so that the overlapping part of their communication disk will be small and number of conflicting RX users will be decreased. In this way, the potential collision, which can also be referred as cross-influence of multiple TX users, can be reduced. Mathematically, the cross-influence on the RX users brought by two TX users J and J prime in the time slot I can be evaluated by where minus 0.1 is 0 is small enough. Therefore, the average cross influence brought by user J in time slot I is given by like this. The total cross influence with respect to time slot I can then be obtained easily. We refer the matching problem here as MD geometric SR problems. Rotation matching problem for MD geometric SR problem. If there is no matched forbidden pair, the final matching, we say no. We then say that it is a feasible solution. Phase 1, obtaining a feasible solution. We utilize a greedy algorithm in which each user is assigned with one time slot. If a matching problem is solvable, For any unmatched user J, the set of available match time slots denoted as where T matched is a set of matched time slots, and HJI is a set of users forming forbidden pairs with user J. When row users J selections and then unmatched time slot I. Otherwise, it selects matched time slot I prime such that it brings the smallest cross inference QJI, for example TI, average mean QJI. Phase to rotation matching. We introduced the conception of rotation to better describe the interdependency of different users in the MD geometric SR problem. Definition 1. Give a matching obtained from the first phase with a subset of users NS and satisfy NS R2. A rotation sequence refers for a rotation matching with respect to rotation sequence is defined as like this. To be specific, a rotation matching is generated in which subset of users switch their matches in predefined cycling order shown in line, while other users remain their matches. Considering the complexity of the algorithms, we set the length of the rotation sequence L max. The optimality and the validity of one rotation matching are shown below. Definition: to consider a matching and subset of users NA and with size L for 1 and L-1. A rotation matching is valid if any user J does not form forbidden pairs with any matched pairs in like this. Rotation matching is optimal if it achieves the smallest average cross inference in sevens, with no forbidden pair among the matched pairs. For example, definition 3. MD geometric SR prime matching is a rotation stable if rotation matching are optimal. For example, no rotation matching with L max can further reduce the average cross inference of. Description of the whole algorithms. Given the above definition of the rotation and stability, we then propose a TX-RX selection and time scheduling algorithm UTSA to obtaining a L rotation stable matching as listed in details in table 1. To start with, the BS collect each user's geometric information to construct a forbidden matching list of each user. In phase 1, feasible matching is obtained by the BS via greedy algorithms. Phase 2 contains multiple iterations, in each of which an optimal rotation matching is executed by the BS given randomly selection rotation sequence. The iteration stops until no rotation sequence can further reduce the total cross influence of the network. Third, multidimensional stable roommate matching for the subchannel allocation. We now extended the above algorithm to solve the subchannel allocation problem in each time slot. We reconstruct the utility function based on 4 to formulate a non-convex integer programming problem, which is much more interactive than the time user matching problem. Definitions. We observed that the set of TX users and subchannel can be considered as student and rooms in an MDSR problem, respectively. Denote the set of the TX users in each time slot I and T, and the set of subchannels as K. In each time slot I, a user subchannel matching is then defined as mapping from set N K not into itself, such that K each TX users can match multiple subchannels. Each TX users can match multiple subchannels, and each subchannel can match multiple TX users. utility functions different from geometry utility function in 7. We further evaluate the code channel cross inference based on the number of successfully decoded signals. For any TX user, J its utility with respect to subchannel K is defined in, for example, the optimal rotation matching for a subset of TX users and S and T in time slot I can be written as like this. With the above definition, the modified rotation matching algorithm is shown to table 2. In the centralized SPS scheme, the BS performed the above two matching algorithms sequentially. The convergence and the stable of these two algorithms can be guaranteed based on definition 3. NOMA-based distributed power control. In this section, we address the NOMA-based distributed power control, in which power control program is formulated for each TX user and the control signal between the TX user and RX user is considered. To perform SIC decoding, necessary prior knowledge needs to be provided to the RX users. The CSI of the intended TX user and RX users links the number of transmit powers of the corresponding TX users. Therefore, the distributed power control requires information exchange between the TX users and the RX users. For example, the control signaling, we divided each time slot into one control signaling sub time slot and one data transmitting sub time slot, in which the control sub time slot is divided into several pairs, TX blocks and RX blocks for control messages exchanged between the TX users and the RX users. Each pair of TX block and RX block iteratively works as below. TX block, every TX user J broadcasts a reference signal to its neighborhood containing the transmit power and then frequency resources that it will occupy for the data transmission. The transmission power Pj is determined based on the feedback sent by RX users in the previous block. Each RX user obtains its neighborhood TX user's CSI via received reference signals. RX block, each RX users evaluate the user it will successfully decode the coming data messages based on the information obtained from TX block. It then calculates the potential co-channel interference to each TX user J caused by other TX users and broadcasts the feedback for further processing in the next TX block. The power control program of TX user J over subchannel K in each TX block of the time slot I can be formulated as below. Where P is the maximum transmission power, TX user J over subchannel K is a set of RX users sending feedback to TX user J during the RX block over subchannel K in time slot I. Wj is unique overweighted value for each TX user, constrained 12 guarantees, 8 guarantees that the cross-inference caused by the multiple TX users can be constrained to tolerable level. Problem can be solved utilizing the bisection method. Simulation result. In this section, we consider the urban scenario defined 5. The average inter-vehicle distance is the same lane as is to the 5s x speed, and the same density speed in all lanes is adopted. We evaluate the performance of the proposed NOMA HCD schemes compared with a traditional OMA-based scheme and NOMA-based geometric grid algorithm, NOMA GGA. NOMA-based scheme. On each TX users transmit a maximum power. The TX RX selection is solved by utilizing a grid algorithm, and then graph-based method in 10 is performed in the subchannel allocation. NOMA GGA, we adopted the geometry utility function 7 in the centralized SPS for both time and the frequency resource allocation, where grid algorithm is adopted. Major simulation parameters are listed in table 3. We consider the length of scheduling period of 40 milliseconds for simplicity here. The number of sub-channels is set as 5 in the NOMA case and 10 in the OMA case, respectively. Figure to illustrate the PRP versus the speed of the vehicles where the communication range of interest is 150 meter and the most TX users share the same sub-channel. In the simulation, we consider packets successfully received only when the latency requirement is satisfied. We observe that when the speed increases, the density of users decreases in the network, and thus there is less potential collision, leading to the increased PRP. Furthermore, the gap between OMA-based scheme and the NOMA MCD scheme becomes smaller as speed grows, indicating that the non-orthogonal manner of the resource utilization works better in a dense network. Figures represent the latency satisfaction ratio versus the decoding rate of threshold RTH with the Kmax equal to. The latency satisfaction ratio defined as the ratio between the number of successful transmitted packets satisfying the latency requirement and the number of successfully decoded TX user given the decoding rate or SNR threshold. The latency satisfaction ratio increases with the decoding rate threshold since the decoding rate threshold becomes closer to the required transmission rate for low latency. From figure 3, more TX users can satisfy the latency requirement in the NOMA case compared to the OMA case. This is because the spectrum efficiency of OMA cases is lower than that of NOMA cases, leading to higher transmission delay. In this paper, conclusions. We studied the scheduling and then resource allocation problem in cellular V2X broadcasting system to reduce the access control collision and improve the reliability of the network. We proposed the NOMA-based mixed centralized distributed scheme in which time frequency resources can be fully employed in non-orthogonal manner by the BS while the dynamic power control along the iterative control signaling is autonomously performed by the vehicle to achieve a better performance of power domain multiplexing. Simulation results show that NOMA MCD schemes outperform the OMA-based scheme, especially in a dense network.